Thank you for having me. I'm excited to be here. So today I'm going to talk about our work in advancing agentic intelligence. So my name is Joseph Gonzalez, and I live at the intersection of two very much colliding worlds as both a professor and an entrepreneur. As a professor at UC Berkeley, I'm one of the co-directors of the Sky Computing Lab. We're developing the next generation of advanced AI systems. And I'm also a member of the Berkeley AI Research Group, or BEAR. We're developing the next generation of AI technologies, algorithms, and models. I've been fortunate enough to be part of some really exciting projects at Berkeley. My students launched some of the first chat-enabled models with the work on Vicuña. And then building on those models, we launched the Chatbot Arena, which is one of the most widely used open platforms for model evaluation. More recently, we've been thinking about tool use, and the Project Gorilla has been looking at how we both discover and invoke tools to find the right APIs to accomplish complex tasks. And building on that, we launched the Berkeley Function Calling Leaderboard, which has become the standard platform for evaluating function calling capabilities in models. My group also did pioneering work on the design of agents, and in particular, how we bring memory subsystems into agents to allow them to have long, complex conversations. And today I'll talk a little bit about some of the work we've been building on top of that project. More recently, my group has been focused on the design of systems around post-training, that is supporting supervised fine-tuning and reinforcement learning to enable reasoning models and other kinds of behaviors. And so these technologies have made it easier for us to develop new kinds of model add-ons or new model capabilities. And then at the system level, my group has been developing the open systems for serving models. From the projects like SGLang and then more recently VLM, we've built the standard tools that people use to serve open source models across many industries today. As I said, I'm also an entrepreneur. I'm a co-founder at Run LLM, where we're building the next generation of AI support engineer agents, so developing agent technologies. I'm an advisor to Genmo, a company building open video generation models. I'm also advisor to Leda, which is a company commercializing our work on MemGPT to enable more stateful agents. As part of a collaboration with my colleagues at Run LLM, we've been writing a blog series called the AI Frontier, which I have a QR code here, and I highly recommend. We have written over 100 blogs. In fact, last week was our 100th blog, looking at the intersection of AI, product design, and how we build technologies and take them to product to industry. And the last blog looked at the evolution of what we predicted would happen and what's evolved in the past several years. So today I want to talk about the rise of AI-powered agents. So for me, agents are AI systems that combine reasoning and tool use to accomplish complex tasks. At the simplest, we can think of it as an LLM interacting with some software services or systems. Though increasingly, it's also interacting with data technologies through things like RAG to find the right information. And as we move forward, we start to think about things like context management systems that manage the memory or context that's exposed to the model. And then very recently, there's been a lot of excitement around being able to build specialized models using all of this post-training work that can adapt to specific domains, have specialized capabilities. And today, I want to convince you that there's significant opportunity for innovation on the right side of this picture, that we don't all have to be developing the core foundation models, that in fact, a lot of the exciting work and maybe the really disruptive work in research and in industry will come from this yellow box. So today I want to talk about three exciting efforts for my group. These are relatively new efforts. The first is on sleep time compute, and this is allowing memory agents to reflect on conversations between interactions, enabling reasoning between invocations, between test invocations. The second two I want to talk about aren't even published yet. So these are work that's ongoing, will hopefully be on archive in the next few weeks. The first is user agents. And this is learning human preferences by learning to anticipate what a user will say. In a sense, building a digital twin. And the second is advisor agents. This is learning to guide black box models through complex tasks from reward signal. So let's start with sleep time compute. So again, this is joint work with colleagues at Leda. And many of you have probably already heard about some of the excitement around test time compute scaling. the idea that using more tokens, I could build a richer context that could allow a model to answer a question more effectively. And this has been a big boost to what we can do with AI, but it's expensive and it increases latency between when a question is asked and when an answer is given. So we started to wonder if we could get the benefits of test time compute without the limitations. And our key insight as we think about this is the idea of background inference, being able to reduce latency and cost. And we do this with what we call sleep time compute. So it's bringing in mechanisms to leverage computation before and in between interactions. This allows us to anticipate requests and compute useful quantities before the query ever arrives. And then if we get many questions about the same context, to be able to amortize that compute across queries to reduce cost. So here's a simple depiction of how this works. Imagine you're solving a math problem, as many LLMs do these days. There's often a significant amount of context around the question. The parameters, maybe there's a juggler, the balls, the quantities of things that they're juggling. All of this context is presented up front, followed by a question. And in the normal test time compute regime, you take the context in question, and then you think about it, generating thousands of tokens before you arrive at an answer. In the sleep time compute setting, we iterate on that raw context before the question ever arrives. We compute useful quantities that could then guide the final conclusion at test time. And ideally, we've computed most of what's needed so that at test time, we can only do a little bit of computation to get to the final answer. So we try to formally describe what's going on with sleep time compute. Suppose we are given a context C and some query Q. The context C could be a collection of documents. The query is maybe a question about those documents. If we look at traditional test time compute, the idea is that we're taking the context and the query and computing an augmented context. And this can be used by the model to answer questions more effectively. And this is an answering step where we then take that final context to produce the answer. The idea with sleep time compute is that we're going to construct this augmented context only using the initial context without the query. And we can reuse this amortized sleep time compute context across different questions. So that at test time, we can take this context, append it to the query, and get a final answer without the need to make another sequential decoding call. So in practice, it allows us to be both more efficient and reduce costs. And we do this using an agentic loop to optimize the sleep time context. And this is building on this memory architecture we developed with the MEMGPT project. And I think this points to this bigger idea of how we manage context more effectively by giving a model tools to allow it to move information out of the conversation into long-term and short-term memory, and then pull those memory facts back into working memory as the model proceeds through tasks. With sleep time compute, we prompted the model to prioritize the information over existing memories, to consider how the information affects previous memories, and to use reasoning to identify logical conclusions and potential hypotheses. This allows us to scope what we produce in this sleep context to help the model most effectively. So to evaluate this, we developed some new benchmarks extending some of the standard mathematical benchmarks to introduce additional symbolic state both up front and then to reuse some of that state across different tasks to test the scope of what can be achieved. And so when we do this, we can reduce test time compute by up to 5x at the same accuracy. Because again, we can do all this pre-processing. We can also increase accuracy by 13% when the budget isn't constrained. So we can do additional computation on top of all this sleep time compute to get further high quality results. And then if we have lots of questions around a similar context, we can see significant reductions in cost, again, by amortizing this context across queries. So there are a lot of opportunities for sleep time compute. I want to highlight some of the important use cases. In software engineering, the context C could contain the entire repository that we're reasoning about. So if we are processing it at sleep time, we could summarize the structure, identify patterns and issues that could help address future bugs or questions. For document question answering, the context contains the documents. And then the sleep time compute could help identify important facts and relationships that we could infer from those documents. And then for long conversations, the context C contains the memory in the previous dialogue. And again, we can think of the sleep time compute as anticipating what might be said, refining our understanding of the previous conversation, and maybe guiding towards an answer that would be most appropriate for the given user. So in fact, the work on this, on sleep time compute, got us to start thinking about user agents and how we might be able to learn how to respond for a particular user based on interaction with that user. So your user agents are allowing us to learn human preferences from interaction. So we think of how we currently learn a preference. A lot of the work builds on this kind of binary comparison of two agents, of two responses. So if I have a response A, a response B from an agent, which one does a human prefer? But if we think about natural conversations with a human, the natural form of interaction in something like unstructured chat, we don't get this binary comparison signal. And so the research problem we explored here is how can we learn this human preference from unlabeled data, from these direct chat interactions? What we've proposed here is unsupervised preference learning through user agents. And again, these agents are going to act like digital twins of the user. So here's a big idea. So imagine one of my grad students is trying to draft an email to me and they have an AI helping them write the email. It writes a draft and they might give some feedback like, hey, make it less formal or more concise. It gets another version. They might say, hey, that looks great. In this conversation, they've revealed preference information about what they look for in an email to their professor. And now grad students using this thousands of times a day, or at least a week, they collect a large number of these conversations for any one user, for any one graduate student. We'd like to be able to automatically extract the preferences from those conversations, in a sense, to build a user model that can answer the question, what do I prefer, A or B? So we sought to make this work using the sort of standard techniques you would imagine in post-training today. Our goal here is to teach a model to complete the user's turns consistent with their given preferences. And we start with something like supervised fine-tuning on user turns. We have all these dialogues, and now we're teaching the model to not respond as the agent, but to respond as the user. And we did this, and it actually is kind of neat. It starts to sound not like a helpful agent, but like a demanding user looking for progress on its problem. But it doesn't yet capture the user's preferences. So we found a way to solve this by augmenting the training data with contrastive examples where when the user gave one piece of feedback, we can synthetically generate other feedback to contrast against, and then use something like DPO on these user turns. So this actually starts to sound more like the user and captures the user's style of responding. But unfortunately, if we do this, the model doesn't yet have the ability to answer questions like which response is better, because again, those kinds of questions are pretty out of domain. So we found a simple solution here. We can use our earlier synthetic data set to then generate multiple responses from the model, and we know which one was created based on the feedback that the user originally gave. And now we can also create some examples of this binary preference signal. So putting all these pieces together, we can build a model that actually can respond like a user and even answer questions about a user's preferences just from conversations with the user. And if we compare that preference scoring, so 50-50 being just guessing, which is what a baseline model would have, and then even against in-context learning where we show some examples of what the user prefers, combining these other techniques, we can get a significant boost in accuracy and our ability to infer the preferences of that user. But maybe more interestingly, we can now simulate a user. So a user might ask for something, the base model can generate a response, and our user model, our digital twin of the user, can provide feedback in an iterative loop before the human ever actually sees the model's output. And then after this iteration process, we can give a much better revised response, again, by simulating human preference. So this work on modeling human preference got us starting to think about maybe there's a way for models to give other models signal to guide them through a process. And so the last thing I want to talk about is learning how to guide a black box model through complex tasks. So we call these advisor agents. And we're going to, again, use these learning techniques, in particular reinforcement learning, to teach a model to help another black box model complete a task. So we think back on how agents learn. There's some flaws in each of the approaches. The standard approach in context learning or prompt engineering relies on carefully constructed prompts and examples to guide a model to address issues to solve a problem. But this is brittle and requires significant manual effort to find these examples and provide the correcting feedback needed for a model to succeed. The other approach, which is pretty exciting, is post-training. We use supervised fine-tuning or reinforcement learning to augment the LM with new behavior and knowledge. But this approach is pretty sensitive to variation in domain. It can lead to things like mode collapse or loss of instruction following or other kind of general behaviors that we need in our base model. So we thought we could try to combine the best of both worlds to use both in-context learning and post-training in a way that preserves the advantages of in-context learning and post-training. So here we're going to use reinforcement learning to train a second, smaller advisor model to adaptively prompt a stronger black box model. The idea here is we're going to retain the original model, the general instruction following capabilities of our black box model. And this could be a state-of-the-art model that we can't even train in the first place. And it's also going to eliminate the need for prompt engineering because we're going to learn to construct a prompt based on the current state of the conversation. So this is a conditional prompt. And we're going to do that from reward signals. To show you what this looks like, I might ask a model, help me write a review for the book Frankenstein. The advisor could jump in and provide additional information. And again, if you think of the work on user agents, that's a kind of an early example of an advisor, giving advice to the base model on what I might prefer. The model generates a response, and again, the advisor can look at the output of the black box model and provide even more contextually aware guidance. For example, provide more historical context, so that the black box model produces a result that's again consistent with the end goal of the user. So to give you an example of how this works, so we have a small open source advisor model, and we're going to use this smaller model to guide our larger black box model. We let the black box model generate a response to some given user prompt, and the advisor model is going to look at that and provide natural feedback, and in a sense, iterate with that black box model. And when this process is completed, the resulting output, the final outcome, is given to the user or maybe iterated on in a bigger agent loop. And then when a reward is finally computed, that reward is sent to the advisor model. We're unable again to train the black box model, we're leaving it fixed. We are tuning the advisor model to give feedback to the black box model that is more optimal for the reward or the desired outcome. So here the advisor model learns to guide the black box model to maximize reward. And it allows us to preserve the general capabilities of that black box model. And again, this is critical as many of the post-training methods often change how a model behaves, especially in out-of-domain tasks. So we early results on this, and here we're going to compare against GEPA, which is one of the other techniques developed from our group at Berkeley, thinking about how to augment prompts using genetic algorithms. Here we're again going to use the reinforcement-based approach, where our advisor is this Quen 2.57b model. It's a small model. And our black box model, the one we're going to guide with our advisor, is GPT-4o mini. And if we look at three different preference tasks that we created, length, level, and pick versus choose, which are simulating different kinds of latent human behaviors, the advisor is able to very quickly dial in on what is it the user wants, just from a reward signal now, and then use that information to guide the black box model to get to the right answer. So I find this pretty exciting because it allows us to now use reinforcement learning in a new way, in a way to construct prompts or to search the space of prompts or conditional prompts more effectively. All right, so I've highlighted three directions that I think are really exciting and sort of speak to this effort or this opportunity in how we advance the systems around the LLMs that we're building today. And now I want to take a moment to look to the future and talk a little bit about what this could mean as we build these systems, not just for agents, but for humans. So we go back to this picture. I've made this case, I hope, that this yellow box has an enormous opportunity for innovation. And those innovations can happen while we leave this black box, the LLM, fixed. But that also means that I can replace that black box with a human. And in many ways, these same innovations should also help a human accomplish tasks more effectively. So things like agent memory could be there to help a human organize their context, the interactions in a way that is more helpful to the task they have at hand, and then maybe even capture things from their actions to be used in the future. This idea of sleep time compute offers the opportunity to think about recording the past, thinking through it between and before interactions in the future, and then using that additional offline reasoning to really augment what the user is presented when they encounter a new situation. I like to think of, I meet with many students throughout the week. What if the sleep time compute could analyze my previous conversation? So when I get to the first meeting of the student the next week, I have a lot more context that's been enriched by reasoning about the past. We think of user agents. Imagine if we could model ourselves in complex situations. This could not only allow us to simulate how we might respond, but also help us respond to things more effectively that reflect how we as people would encounter or would respond in those situations. And then finally, advisor agents, building models that can then guide humans more effectively from reward, knowing when I succeed and when I fail. I don't necessarily have to learn anymore. I can allow an advisor to provide guidance based on the signals it captures, given the context that I've accumulated. So I think this is pretty exciting for an organization like Samsung because in many ways we at Samsung are building tools that interact with our environment that capture a lot of this rich context, both on our bodies and the devices we interact with in the world. And I think that context will be critical to really enabling humans to benefit from many of the advances that we're pushing in the systems around AI. And so being able to read email, messages, audio, video to capture that in a secure way on the device so that all the interactions I have are recorded in some way that I can then process. This opens up really exciting opportunities for things like a memory agent that could surface the right information to humans as they need it. Uh, it gives me a chance for advisors or user agents to model how I would respond and also guide me through complex processes, help me achieve my goals more effectively. And things again like sleep time compute could run in the background on these devices, allowing the down cycles to be used to really understand my context better so that when I encounter a new situation, there's significant thought that's gone into my context to help me succeed in that new context. All right, so I want to conclude by saying that there's a lot of exciting things happening in the space of agentic intelligence, and the innovations really in this systems and AI interaction. And I think that will advance AI capabilities, but I think it also really opens the opportunity to advance human capabilities. And with that, I thank you, and I'm happy to take questions at the panel afterwards.